About structs, we saw syntax for structs. We were able to create struct instances. We were able to use those instances. We ended the lesson building a complex structure. We called it fellow. We modeled a fellow with properties. We gave the fellow 2 instance methods, right? So that was structs yesterday. So we saw structs will enable us to have more complex data types in our programs. Today we'll see classes. Classes is very similar to structs in that instance, right? It enables us to build more complex data types, right? We saw enums a couple days ago. Yesterday we saw structs. Today we see classes. So those 3 objects enable complex applications, right? Applications you use, whether it be Instagram, right? Twitter, right? Those are built using all those structures, classes, and enums that we saw and including today, right? There's differences, there's subtle differences between them. We'll talk about those differences. We'll revisit those differences. We'll see those differences in code. Knowing those differences, especially between structs and classes, is very vital. Vital now, vital at your job, before the job, at the interview, right? Knowing the differences and being able to explain the differences is very, very, very important, right? So again, classes, we'll see today, enables us to have properties, methods, right? Emulate real-life objects into code, into programs, right? Yesterday we did that with fellow. Today we'll use different instances of real-life objects to create classes. So let's go to playgrounds. Create a new playground. You could call it classes, right? So classes will say our building blocks that enable us to create complex objects in our program. Those objects are created using properties and methods. Right? So again, very similar in the basic construct of it with structs, but we'll see the differences very soon into the lecture between classes and structs. But keep in mind that Apple highly recommends anytime you start a new object, right? We spoke about object-oriented programming yesterday, right? We said object-oriented programming enables us to encapsulate real objects into programs using properties, methods, right? So when you start a new project, for example, you have some game you want to create, start it out with a struct. That's the default. Apple recommends it as the default. Structs, as we see yesterday, is immutable by state. It's very similar to having a constant. As you want to create some data store, you start with a let. As you go through the program, if you want to mutate it, you change it to a var. Everybody with me? Okay, so that's like the basic default. You start doing it, a let or a struct. So we'll see the syntax of a class. So class syntax. We start out with the class keyword. So Apple makes it very easy, right? So you want to start a class, you start with the class keyword. You want to start an enumeration, you start with the enum keyword. You want to start a struct, you start with the struct keyword. So it's not too much guessing there as far as like how you get started. Cool. So we need a name. So we'll start out with a name. It's going to be uppercase, like we said yesterday. For our custom types, we need to have uppercases, right? It's not a compiler error, but it's coding style. Everybody with me? Right? Do not submit code where you have a class name with a lowercase m like that, right? So you want to say my first class here, camel case, everything uppercase. So as is, this is a valid class right now. Yes, it doesn't have any information in the definition for now. There's no properties, there's no methods, but that's the basic syntax of a class. You start with the class keyword, followed by the class name, followed by open curly and close curly. Great. Immediately, let's jump into the first difference between a class and a struct. Here we'll talk about inheritance. I think somebody yesterday brought up inheritance. I think that was Greg. Loosely, he brought up inheritance, right? Structs do not inherit from other structs, period. You get asked that on an interview? No, does not work, right? Structs do not inherit from other structs. Only classes can inherit from other classes. When I say inherit, I inherited, right? I inherited traits from my mother, right? Also, maybe my great-grandmother, grandfather, right? You inherit certain traits, right? I'm susceptible to diabetes, right? The good, the bad comes along the way there, right? You have your parent, you get the good, the bad, right? You can't change that. It is what it is. So you inherit the good and the bad from your parent. So here we have a class. It could inherit from a parent class, but a struct cannot inherit from another struct. Everybody with me? We'll talk about protocols in Unit 2. We've spoken about protocols loosely already because we've seen protocols in enums. But we'll talk more about protocols and how you could expand. We saw it earlier. We had an enum. We needed to get more cases on the enum. What did we have to do? Anybody remember? On that enum type, how did we get the cases? I'm sorry? Dot syntax? Yes, sir. Yes, go ahead. Oh, you said dot syntax? What did we have to do on the enum? I had an enum, right? So I had an enum here. Let's do some review real quickly. I had an enum. I said day, and I said case Monday, Tuesday, for example, Wednesday. I heard it. I'm typing and I heard it already. Muscle memory. What's that? Case iterable, right? According to Adan here. The only way to know how many cases we had to conform to case iterable. Everybody with me? So that's the way you extend your struct, or you get more functionality into your struct. You can inherit, like enum here cannot inherit from anything, but it could extend or conform to a protocol and bring more functionality in, right? That's what we spoke about. Cool, so I'll just put case iterable here. That's our introduction to protocols. So they now has added functionality to count how many cases it has. Example here, it is 3, right? So with classes, we could inherit and get functionality from our parent. Right? So inheritance takes us back to inheritance here. Structs cannot inherit, but they could conform to a protocol to get more functionality, right? You start out with an object, you want more functionality of your object, you could inherit if you're a class. If you're a struct or an enum, you could conform to a protocol. Everybody with me? Yes? Here we said they conforms to case iterable. So now our day gets all cases. So day, all cases, like that. Dot count. I could run that. Run, right? And you see we have 3 in the preview outcome. It's telling it now we want to have this property called all cases. Because before case iterable, we would not have all cases. if we were to remove case iterable as we saw, I think you may have missed that class. As we saw, if you remove it, you won't have all cases anymore. So what case iterable did, or what the protocol did, it extended or added more functionality to our enum day. Cool? Very good. Any other questions before we move on? Yes, sir.
So, I'm sorry if I didn't hear it right. What's the main difference between inheritance and conforming to a protocol?
Inheritance, you get everything your parent has.
Okay.
Doesn't matter if you like it or not. Right? I was born, my mother, as I said, is susceptible to diabetes.
Right.
I get it. Right? But if I conform to something, I could say, hey, I only want the good parts of this particular protocol.
So anytime you access a property from that protocol, that's the only thing you get?
In that case, all cases, that's all I want. So I just say, I want all the cases, that's all I want.
Okay.
And then you could go along the way. So it keeps your type easier to maintain, if that makes sense. You don't have all that boilerplate code to worry about. We'll see later, right? As we inherit, there's good and bad to both of them, by the way. As we create an inheritance example, we'll see if we use a function, we have to override it. Like we'll see, we'll get into it. But basically, you absorb everything that your parent has. Everybody with me? Again, we know we all have parents here. We have good and bad traits from them, right? Especially in the blood there, right? And the big C word too, right? All those things, like your family is susceptible to stomach cancer, right? Stuff like that. Then you have to be careful there because it's part of you. It's part, you inherited it. So classes, we said, could inherit, and structs cannot, right? So only classes can inherit other classes. Great. That's inheritance. Let's see what it looks like. So I'll start out with a class. I'll call it person. Right? Person here is pretty generic. We all could classify ourselves as persons, people, right? A person or people, including Prince at some time, right, have a name, right? No matter how you change it, you got to be called something. We have an age, right? So those we saw yesterday, those are called what? What type of properties are those? Stored properties. Very good, right? So those are stored properties because name has, whether or not you believe it, it has a value already. Everybody with me? Right? We defaulted it to some value. It's an empty string, but it has something in there. Right? So that's a stored property. So far, so very similar to structs. For now, just minus the name, nothing is different. Even instance method, you could have instance methods here. Here we'll have some instance method, we'll call it info. And we'll say print, this class, this is a person. Great. So we have a class person, it has two properties, name and age. It has an instance method called info. Let's go ahead and create a second class. Here, we'll create fellow. And syntax is very similar to conforming to a protocol, right? Fellow colon, the class you want to inherit from. In that case, I want to inherit from person. So this is the syntax for inheriting from a class. So here, fellow inherits from person. Basically, fellow is me. I'm inheriting from my mother, right? Terminology. So fellow inherits from person. Fellow is a subclass of person. Person is the parent or superclass of fellow. right? Great. While keeping everything on screen, let's create an instance. So here, creating an instance of fellow. And we said creating an instance is you're actually creating a variable or a constant of that type, right? That's what that means to create an instance. You're creating a variable or a constant of fellow. So you're saying let var, or you're saying let, well, not let var. You're saying let fellow name or var fellow name, right? So you're creating a constant or a variable of that fellow, from that fellow. Cool, great, 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 great. So here we start off, we say we have Brendan is a fellow. Right? And here I could say Brendan dot. Look at that. So let's step away for a second. Our fellow doesn't have any properties, correct? Our class is empty. Everybody sees that, right? There's nothing in our class right now. In our fellow class, it's empty. But I created a fellow, right? I created a fellow. I said Brendan dot. And look, I inherited the properties of my parent. I have age, I have info, I have name. Do we see that? Right? So that's what we mean when we say inherit, right? You inherit the properties, all the properties, and all the methods of your parent. You can pick and choose at birth. We might wish we could, but we cannot. Maybe at some point, they'll figure something out there. Yes, sir.
Does it also inherit the values associated with those, or
just the properties? Yeah. Just the properties. And if your function has, in our case, this is a person, if you print it out, it's going to print out this is a person. Okay, but if there's default properties, it's going to take it, sir. If there's default properties, like stored properties, it's going to have that value. All right, so here we have Brendan. We say Brendan.name is Brendan, right? And now I could say Brendan. Again, our fellow is empty, correct? We have no code in 38. So far, so good? But I could still say .info because my parent is person. Person has an instance method called info. Do we see that? Okay, cool. So here I could say Brendan.info. I could run the code. And look, I see this is a person here. Everybody sees that. This is a person. Obviously, fellow is a person. So I come in here. It's an instance method. So the instance is Brendan. Brendan calls info. Info gets called, and this print statement gets executed. So far, so good? Great. What's that? You have a question? Oh, yeah, go ahead. If there's a property name here, like this, then you have to override it. Let's hold on that for now. Okay? Let's talk about overriding later. Let's hold off on that. Let's get incrementally into it. So here we have an instance Yeah, sorry, go ahead.
So you got to create an instance of person in order to create Brendan.
An instance of fellow.
Or you had to create fellow in order to create.
Okay, let's backtrack, right? So we started out with a class. The class was called person. So far, so good?
Yes.
Okay. Person has properties. It has two properties, and it has a method. So far, so good? We created a class called fellow, right? It's a template. One, right?
That's also a class.
That's a class, yes.
Okay.
That's a class. Again, only classes could inherit,
Okay.
right? So we have fellow. Let's read it the way it should be read. We have a class called fellow. It inherits from a class called person. You with me? Okay. Now, if my fellow inherits from a person, as we know, the basic meaning of inheritance is you get the traits from your parent. You with me? The traits meaning I get everything my parent has. My parent has name, age, and info, instance method. Correct? Right. So now I could go ahead and create an instance of fellow, not person. Right? This here says fellow, not person. You with me? Right. Okay. Now fellow, because it inherits from its parent has a name, property, its parent has an info method. You with me? I could go ahead, create an instance of fellow, call it Brandon. Say Brandon.name, assign Brandon a name. And now I could say Brandon.info, and it will say this is a person. Yes, from its parent. Right? Yeah, you don't have to. You don't have to. Like in my case, I haven't used age yet, but it's available if I want to use it. Is that good? But yeah, so if we were to, let's make info a little better. Yes.
I was going to say you can only do that with like one class.
Okay, so a class could only inherit one single inheritance.
Okay, it can't be passed through one class to the next class.
You could go to a next class that inherits fellow, right? But let's write that down, please, as you brought that up. So in Swift, we only have single inheritance, right? Meaning you can only inherit from one parent, right? So fellow cannot inherit from person, comma, somebody else. Everybody with me? In some languages, that's supported. I think C++. But in Swift, single inheritance. Less to worry about. Yes, sir.
So Brandon is still the
Yeah. If you instantiate a person, it would be a person, right? But we'll add more properties. Like I could extend on what my mother gave me, right? By having my own properties, right?
You can't append, like you can't add any new properties to the mother.
As the child, no.
No, but you could call the mother.
Yes, like you get everything the mother has plus whatever you yourself have.
So even if you added more properties to the mother, then those properties will still be accessible by the.
Yeah, you can. I mean, we could add more things here. Like I could add whatever well status or whatever I could add here. I could add more things. Whatever I add here, the child is gonna get it, right? It's like you recreated your parent, right? If you were to recreate your parent with whatever traits, you're gonna get recreated too. Does that make sense?
Right.
Yes, sir.
Everything inherited by a subclass, type methods, type properties, as well as
Instance methods or everything. If you don't want to have anybody inherit from you, you have to mark yourself final. We're not going to talk about final today, but again, your parent, you take everything from your parent. Okay? It's just the nature of nature, I guess. We inherit everything from our mother, dad, right? Does that make sense? Yes, sir.
let's say we didn't do
But it's up to you to use whatever you want to use. Yes, sir.
how many properties does fellow have right
Fellow, how many properties does fellow have now?
now? Name and age, right?
How many properties does fellow have right now, as it stands? Its own properties. 0. It doesn't have any properties right now.
So it's taken from person, right?
I'm sorry?
It's taken from person,
It's taking it from person, from his parent.
which has 2. So Brandon currently doesn't have an age in his,
Because we haven't explicitly accessed the age.
but we have to.
You don't have to, it's up to you.
Okay, yeah.
So let's go ahead and print out the default. Let's go ahead, go back to your string interpolation here. Go back to info and say this person, let's give it the age and the, so this person name is name, and age is age, right? All right. So we make use of both properties on person, and let's go ahead and give person a default name. We love, let's do Jane Doe. Age, default 21. So we've updated the person with better default values. Default for name is Jane Doe, age is 21. As it stands, the person's name is Jane Doe, and the age is 21. Everybody with me? So far, so good. Let's go back and print our info. So now we see this person's name is Brendan and age is 21. Right? Like, let us soak that in a little bit. And there's a lot happening there. As I said yesterday, structs easier as far as like the complexity of it, right? We don't have inheritance and all that stuff there. But now the class becomes more complex. Already we see the class is more complex than a struct, correct? Yes.
So if we were to create sort of
Yeah, we will create it. But I want us to understand the bits and pieces before we go too crazy. Does that make sense? Because that part already, like, hey, we have Brendan here. Brendan is a person. He's also a fellow. Does that make sense? So a fellow here is a person. In computer science, that's how it's related. If something is, you say, a car is a vehicle, right? That means a car inherits from a vehicle, right? So here I have a fellow is a person. You with me? But a dog is not a cat. Is a dog a cat? Right? So they can inherit from each other. But a dog is an animal. You with me? A cat is an animal. So if you could read like that, you think of your objects. You're like, hey, I could start out with an animal class. That's the parent. And create a subclass called dog and inherit from an animal. Right? What does an animal have? The traits of an animal. Right? What's the traits of a cat? See the similarities? So when you're thinking of your objects and how to construct them, that's where we say object-oriented, right? Inheritance is a big part of object-oriented programming. There are 3 pillars to object-oriented programming. Let's actually write it down. We might not go through all today, but if you were to ask, I'm coming to that question, 1 second. Let's just write that down first. Where are we? I'm gonna write that someplace good. Oh, we could write it right here. So, object-oriented programming consists of those concepts. We have inheritance. We have encapsulation. And we have polymorphism. Right? Okay, what's your question?
I was gonna ask, let's say you could put like variable. Can you have multiple with the same? Like, let's say in fellow I have variable name, variable age. And
We haven't spoken about overriding. We'll get there. We'll add more properties and methods in fellow, but I want us to understand as we go the basic concepts. Because if we start building more on top of what we have right now without understanding the basic concepts, we'll get lost. Does that make sense? We're getting there. We're getting there. We'll add properties. We'll add age and stuff. Yes, go ahead. Yeah, let's start from the beginning. Thank you.
And inside we put a function called info.
Mhm.
And the info consists of the name, the age, of the class.
Right. Right. So that name is coming from whatever name you passed in when you created it, when you instantiated it, whatever name you put in there. In our case, we have a default, right? Jane Doe and 21. If I instantiate it without an age and a name, those are going to be the defaults. But Brandon was able to override name.
So when we printed the lower, when we printed Brandon because it's fellow.
And because we assigned name Brandon,
Oh, you gave it a name here. Okay.
Yeah.
Right over with the name.
exactly.
Inherited the variable age.
Very good. And very good use of terminology there. Very good. Cool. That's what I want. I want us to incrementally go through this. Chelsea,
For the,
that's good? Yeah, go ahead.
for where it says class fellow person, how would that be read? Because I wrote
Class
down-
fellow person. This guy?
Yeah.
Okay, so we're reading it the way we're reading it. Did we not write it? Let's read it. Let's write it the way we read it. Okay, so class fellow inherits from the person class or the class fellow, right? The class fellow inherits from the person class. Above,
Just to be sure, when you put the semicolon next to fellow, there's not.
the colon. The colon is the syntax you use whether you conform into a protocol or you inheriting from a class. It's very similar to like having the arrow as you're returning. This is the syntax here. That's just the syntax. It tells the compiler what your intention is. So the compiler, again, like we're not doing compiler design, but as you write a compiler, it sees class, it understands what it should be looking for. After class, it should be seeing a name, right? If it sees a colon after the name, it's like either you inheriting or you conforming. If it's a struct and you're trying to inherit, it's going to throw a compiler error. If it's a class and you're inheriting, meaning you have an X class after, it's great, it's perfect. So it gives the compiler information, so it does its parsing. Yeah.
What would it conform to?
This is not conforming to anything. Conformance we spoke about earlier in our enum review here. We said our enum, same syntax, colon, conforms. Yes, so let's write that here. So enum day conforms to case iterable. Right? And we'll talk about more what conforms mean and we'll understand it. But basically here, conform means to get more functionality into the day. And that functionality gave us the all cases, right? So conforming, you could say adds more functionality. Cool? Question? The data, it's a protocol. It's a protocol. So if you option click on it, you'll see it's a protocol, right? It's not a data type per se. It's a protocol. It's a template. Something that's built in, yeah. Yeah. But we'll talk more about protocols later. But it gives us added functionality. It's like having an iPhone and you have a battery pack to it. Now you have more battery. Cool? No. Class is a class. No, that's fine. We have colons, right? We're differentiating what the colons do. The colon could either conform, in our case here on 16, or inherit, in the case of fellow inheriting person. Cool? Back down. Yeah, let's go down. Yulia, that question. We spoke about encapsulation yesterday when we introduced object-oriented programming. Encapsulation basically is that object, its properties, its methods, its initializations, right? So you encapsulate all the properties of fellow in an object. Like you trap them or whatever, right? There's more to like proper encapsulation because proper encapsulation, you have to use private access modifiers on your properties and access them externally through methods. Could write that down, but we'll get more understanding what that means as we go more depth into access modifiers, which we haven't seen yet, right? Private, we don't know what that means yet. We'll get there. But that just gives us what it means. So like proper encapsulation, you have your object fellow, right, Yulia? You have your object fellow. It has properties, methods, initializers, but your properties should be private for proper encapsulation. But for now, just write what we have, and that's where we headed. So when you're trying to explain object-oriented programming, you have to basically, at the end of the program, not at the end of Unit 1, right? There's so much happening. Not even at the end of Unit 2. But by the end of the program, you should understand everything I've highlighted there and be able to comfortably say what they are. Okay? Does that make sense? That's where we headed. Because somebody's going to tell you, hey, explain OOP to them. And you have to really go down and talk about what it is this way. Polymorphism we'll talk about. I'm not going to. The only way I could show that or talk about it is by example. It's a very hard concept to understand. And even when I show the example, which I might not show today, or Monday, we might see it as we go, or we will see it as we go through the program. There's just certain concepts it's harder to see, just talk about it, right? But basically, polymorphism is changing the form of an object. Just writing that down, what does that even mean, right? Basically, a fellow could be a person, and a fellow could be a fellow. Depends on the context of that fellow. We might show it, but again, I don't want to start losing us there. Cool, everybody? So at least write down the concepts. Offline, you could read about them, but they're better done in demo. Everybody with me? Encapsulation, we've done. Inheritance, we've done. Polymorphism, we might do today or Monday. But understand that those, you'll understand them more and more as you keep coding. Everybody with me? Cool. Hands up. Yes.
I was thinking, like the class or enum or any of those, they can only conform to a protocol.
They could if they want to. If you want to extend that type.
Right.
If I want to be able to count my cases on an enum, I could conform to case iterable. Cool?
But it would only be a protocol, that's what
Yeah, you only conform to protocols. Very good. So language-wise, yes, you got it right. You could only conform to a protocol. You inherit only in classes. And structs could conform to protocol. You could conform to multiple protocols. And inheritance is single, right? We wrote that down, right, somewhere? So Swift, single inheritance. Again, that could be a question, right? Is the language single inheritance or multiple inheritance? You say multiple inheritance, they're like, well, let me see your instructor. What is he teaching you? Okay, cool. Let's keep going. Any other questions? Okay, so we have Brendan here. Brendan is a fellow. Brendan has a name. And as we saw, we updated our print to say this person's name is Brendan. And here we overrode what name was. Name was Jane Doe. And now Brendan has his name, Brendan. And he kept the age. We could also change the age. Do we agree? I could say Brendan here. Dot age is 30. Right? And run my program again. It no longer will say 21. It will say 30. We all good with that? You're not 30? I'm sorry.
31.
Oh, wow, I was close. Oh, man, I wasn't trying to get close, really. I should play the lottery today. All right. So Brendan is being fresh. He said he's 31. He aged up. You should be aging down from 21. When you get to 21, you have to age down. Always 21, right? All right. Honesty is very good here. Brendan, there you go. Whoa! That was a hard throw. Too much coffee. Sorry. I should probably go to the Yankees. All right, cool. Let's keep going. We love classes. Oh, everybody is interested in what if we say info here. So start typing in info. All of a sudden, we do have info already. Just trying to rename info. Press enter. And look at that. We're just getting code for free. What's that override thing mean? All of a sudden, we're getting more complex. We did say classes are complex. That's the promise right there. So let's backtrack again.
Wait, when you
Override,
something that's already built in the
yes. Not into Swift, into our type. Right? We have info in our parent, correct? So that's coming from.
Override the info, but I'm saying the override statement.
Override means I'm overriding my parent. Let's talk about it. So start typing info, everybody. Start typing info. We have info. We press enter. If you were to say, hey, I want to have my own info, period, like this, what do you think is going to happen?
It should compile.
Compiler error, right? You see that in code? That's a compiler error. You can't specify the same name without not having override. Because your parent has a function called info already. Everybody with me? So here, let's keep that code and let's say it does not compile. One second. First step, this does not compile. Let's talk about the first step here. Without having override keyword, does not compile. So here, does not compile because parent has the same name, same method name. So fellow needs to use the override keyword. Right? So let's do it again the correct way. Make sure you have that notes there. So now, as I said, if we type in info, we press enter. The minute you type info, that class knows there's an info already in its parent. So you press enter, and the override keyword is given to us because we're saying fellow now is overriding its parent's info method.
Oh, so it will delete whatever the function previously had and put in something.
Yes, so here in our print statement, we'll have something else. Right?
But what if you put the same thing? Then they'll make no sense. That's what you want to say.
I like how you are saying both sides of the question there. Okay, so yes, if you override something and you're not providing any added functionality, you should not be overriding. Does that make sense? All right. So here we overrided info. With the override keyword, you don't have it, it's a compiler error. We agreed with that. Yes, sir.
Would the override function be local to fellow class here, or would that?
That's the looking ahead. After we type it in, we'll see that your answer is indeed true. It does override the info on Brendan. Cool? That was your question?
Does it override it in person?
Yes, it does. Yes.
What if we had another class that was also a person?
We have a class as person already.
I know, but say we had another class, like, okay, staff.
Staff would be a person,
Person.
right? So that's a different subclass. That's like my sibling.
Yeah. And then
Right.
we did a func.
So my sibling employee, which we'll create next, has its own override info. Does that make sense? What my sibling and I do are different. My sibling, what I do and my sibling does are different. Right? If my sibling overrides my parent with the info function, he or she gets his own function.
Yeah.
Right? If they don't, then they get what the parent has. Does that make sense? We'll see that example after. Cool? Exactly. Go ahead, sorry. Yeah, we'll do that. We'll do that next. We're getting there. I know we're eager to go ahead. That's where we're going. All of us are going in the same direction, which is good. All those questions will be answered as we go. Does that make sense? Very good, very engaged. Yes, sir, in the back.
I'm not sure if
The responses are coming. Greg's question was, as we overrided info, will it override that current print statement we have? If we have a new print statement in here, which we will be writing now, does it override that current print statement? Yes or no? Eric? Yes, right? That was the question Greg was asking, right?
But more specifically, is it like a two-way street? Does it actually change the original?
No, it doesn't change the original. It doesn't change. It doesn't change what the parent has.
So it only changes the local.
Yes, I can change what my mother has. I'll try. Always think about it that way, right? When you think about inheritance, right? Can I change my mother's blood type? No.
So when we create a second instance, it would override a function with two different classes, so you essentially have three different
Yes, if it depends on if that third one does override the info. If it doesn't, it gets what the parent has. If we create a staff or an employee class that inherits from parent, and they do not override info, they get what info is in the parent. If they do override it, they get exactly, exactly, exactly. Very good. Good questions. Okay, cool. So we do not change what our parent has. Everybody with me? Good, good, good. So here, let's have a new print statement. We'll simply say this is a fellow for now. At pursuit. Or use name, even better. Like all of a sudden, where's name coming from? Right? We have this class here. Like, where's name coming from? Where did we declare name? Does it compile?
What it compile with, slow down.
Yeah, that's why I put it in there now.
It's still inheriting name from parent.
Yes, exactly. It compiles because of that, correct. Everybody with me? So does this compile? Yes, it compiles. Where does name come from? Where does name come from, Anna?
It comes from the parent person.
Yes, Anna. But
Oh,
we're going to get to reference types. But Anna. Right, so it comes from person, right? Fellow inherited person, fellow has name as well. Cool? We could also say age here. So name is a fellow at pursuit.
wait, this is the boundary for the.
From the beginning of.
No, name and age are variables. So what if we place them inside fellow, is it still going to be a problem?
That would be override again.
Okay.
Anytime you place any property or method inside that subclass, it becomes an override.
So
Okay.
numbers on that are variable.
No, it doesn't matter. You inherit them. Cool? All right, very good. So let's see. So we have name is a fellow at pursuit and is age old. So let's just make sure we use both there. Great. Staying on Brendan, let's go back and just run the program again. Great. So here we see it changed. Everybody? Right? So before we overrode, let's comment this out. We almost forgot what it was before. I will run it without overriding my info. So before I overrode info, this was the print statement. Right? Let's put some notes in there. So before overriding info from before the fellow class overrode info method from the parent class. This was the output from the print statement. Right, so that was the output here, like that, right? This was the output here, a string. Right, so currently, if we just comment out everything in our fellow, right? We comment out everything in fellow, correct, everybody? We get the info print from the parent. We agree? Great. And after overriding info in the fellow class, the print statement becomes comes from the overridden which we do not have yet. So now just go ahead and uncomment out the override function there. So now this is what our fellow should look like. Our fellow is a person. We overrode info. We said print name is a fellow at pursuit and is so-and-so age old. So far, so good. Everybody's up to date with the code. That's good? Keep going? That's good? Oh, the comment. Okay. We updated our fellow, right, everybody? Okay, so I'll scroll down. We could write the notes, and then we will test it out. Actually, we could test it out now while people are typing. So now it went from this person, name is Brendan, right, to Brendan is a fellow at pursuit. Right, so that's the updated print message. And that print message is coming from the subclass. Everybody with me? That print message is coming from fellow. Do we see that? Right? So that's inheritance at its best, right? I could inherit what my parent has. I could override what my parent gave me. Right? That would be a beautiful world, right? Override your blood type or your blood traits. Cool. Yes, the superclass. Did I say parent? Sorry, person. After overriding from the person, sorry. Thank you, Jahid. Right, that is better. Does that make sense? Right? From the person class. But it is a parent. Right? Person is the parent class. Any questions? Mr. Oscar. How are we doing? Questions? Marjette, questions? What part should I go over? Go up a little bit. Here? Okay. You're welcome. Yes. Ooh. I was about to say don't go there, but it did.
Okay, so classes are the only ones that can
Inherit.
form and inherit.
No. Everything could conform.
Okay, but
Only classes could inherit.
okay, and friends.
Please write that down. Make sure you.
I did, I was just trying to
Yeah, but you mentioned it in the statement.
So, and then when it comes to integration, and they also
Conform, yes, but not inherit. Exactly. Cool. Let's flush that out now before interview day. Cool. Are we good? How are we doing with notes? Almost done.
it says only classes can inherit from other classes or the other classes.
You got it? Okay. A lot of things going on. That's why it's good to. When you talk about it, it's better, right? Like as I said, like talking to your fellow, talking out loud to us, right? It fixes like the misconceptions, if that makes sense. Like internalizing what you're doing is not enough. You need to talk about it. So we'll be talking in one-on-ones. Explain to me your code. Explain to me what inheritance is. Explain to me why a struct, why a class. Cool? So good. You're doing all the right things. Yes, sir, in the back.
So the override function, like when you remind us, like a ladder coming down, and then when you call for info, it goes back into the info. But we're overriding the first step.
And in the subclass, yeah.
You can override any of the traits,
Yes,
right?
yeah,
So we like override from age.
yes. But it's not a func, it's a property. Cool? Yes, sir. But yeah, you could override anything your parent has.
Yeah.
Cool? No. Exactly. Let's see. So here, if I have a struct, if I have a struct, Mr. Eric is trying to get confirmation here. So if I have a struct and I call it artist, I call it artist. So far, so good. Right? How we doing? We good? And I have a struct here. I call it pop star. So far, so good. I have a struct, it's called artist. I have a struct, it's called pop star. Right? Two different structs. Now I want to say a pop star is an artist. Right? I want to say a pop star is an artist. So I go ahead, I say struct, colon, pop star, artist. Like that.
So the colon is kind of how you make them equal to each other.
Either conforming or inheriting, yes. Not equal, but it gives the compiler that are you conforming or inheriting. So now compiler says, dude, inheritance from non-protocol artists. So it tells us many things. One, I cannot inherit from a struct. Two, artist is not a protocol, right? So now we saw that struct could only conform to a protocol. Everybody with me? I could simply change struct here to protocol, right? And now this is a different intention. I'm telling my pop star, conform to artist. We'll see protocols. But I'm not gonna go back on that. For now, just keep struct here and know that this does not compile. Chelsea and then, I'm not going back to protocol. I'll go back to protocol in unit 2. Okay? I want us to keep our attention on one thing at a time. Yes?
Did you say that classes can also conform to protocol?
Yes.
Okay, so if it were to do that, since the semicolon makes it another.
In that case, struct here, once you have the semicolon after the name in the struct, this could only be a protocol.
No,
In a class.
Yeah.
A class could inherit, it could conform.
So even if it's not already.
Exactly.
Okay.
Exactly. So here, this is not compiled, correct, everybody? So let's make sure we have that here. Eric, does that help you? So here, this does not compile. So let's keep that here, like that. Does not compile. Structs cannot inherit from other structs.
Has it always been like that?
Yes.
You think they would change it?
No, they should not. Keep structs simple. They're very simple. They're great for working with structs, especially in Swift UI now. It's simple, less memory, right? Faster to work with. Yes, sir.
I know the structs can, or you just said structs can inherit from other structs, but can they be
Oh, wait. Reverse what you just said. You said structs can.
not inherit?
Oh, not. Okay, sorry.
But can they be supervised?
They cannot be. The only way you could extend anything with a struct, anything, is a protocol.
But if class cannot inherit?
No. Because in Slack, classes only inherits from classes. Cool? Extend a struct is through a protocol. Right? Because we saw the protocol part earlier. Right? So if I change a mini, if I change artist to protocol, it will compile. Right? So you could put that there in notes. So if artist is, yes, we will. So if artist is a protocol, you guys love protocols, huh? It's like love the unknown. If artist is a protocol, then code will compile.
That is the same structure with open.
Yeah. Open curly, close curly. A protocol is just a template. You cannot have any extra code in the protocol. It's a template. Like if you're in Java, it's an interface. If you're coming from Java, a protocol is an interface. It's just a blueprint. As opposed to a struct, enum, and class, you could put code in there. You could define a function. Well, you have to define the function. You have to give it a body.
So if I have a protocol
We're gonna get to that. You guys really pulling me that way, but no. Basic concepts. Let's go incrementally. So now we are good with our explanations of stuff. We spoke about overriding. Oh, let's go back and create a third class here. So we have our first class, which is person. We have a second class, which is fellow. Let's go ahead and create a class here. Call it employee. Employee is a person, correct? An employee is a person. Does that make sense? So again, that's how you read it, right? If the thing is a, then it could inherit, right? Right below your fellow class, we have an employee. Employee has its own properties. Employee has a position. We'll default it to iOS developer. Employee has a salary. We'll default that to 85,000. Again, you could write 85,000 like this, or you could write 85,000 like that. Everybody with me? That compiles. It's just easier to read. Great. So now we will go ahead and type in info, override. What's the question? Yeah. So go ahead and override info, and here we say print position is making, position is making whatever, X amount. Put a dollar sign right there. That. Cool. So here we have an employee, two properties. So those are the properties here. Properties. And those are the instance methods. Right? And let's go ahead and create a new employee, a new instance of employee. Everybody okay? We're done with employee? No? Okay, sure. You good? Okay, no worries. Cool? Yeah, we just overrode info like we did with fellow. Different print statement. Cool? Cool? Okay, awesome. Let's get a header, a new header to talk about polymorphism. I'll just touch on polymorphism and show us what it looks like. So go to the very bottom here, and let's talk about polymorphism here. Changing form on an object. Okay, so let's create an instance of a person. Say person. So here, this is an instance of a person. Great. Let's create an instance of an employee. here we have an employee. And let's create an instance of a fellow, or next instance of a fellow. So here we have instance of a fellow. So far, we have 3 classes. We created instances of each type. We started out creating an instance of a person, that's Tom. John is an instance of an employee. And we have Bienvenido here, an instance of a fellow. We could option click and see what type it is. Here we have a fellow that we see here. So Bienvenido is a fellow. If you option click on John, he's an employee. You option click on Tom, he's a person. Do we all see that? Right? We all see that? So here we have 3 different types. We agree? 3 different types. They all inherit from person. Or person is the superclass, the parent. John inherits from person. Bienvenido inherits from person. We agree? Great. So now let's create an array. An array of instances from above. So here we call them people, right? They're all people. We start out with Tom, we have John, and we have Bienvenido. Great. If you option click on people, what type do we think we have? Right. What type? What type? Person, right? According to Mr. Bienvenido here, right? He owns his name. They're all inheriting from person, right? So this is the basic of what polymorphism looks like, right? You have 3 types, but now they changed their form. This people array is not a fellow array. It can be a fellow array. It cannot. Can it be an employee array? No. They all have one similar trait. They're all inheriting from person. We all see that? So if we option click on people here, we see we have a person array. Question is, if we were to loop over the people array, what, for example, would be the info message for Bienvenido? Right? What would Bienvenido message say? In that case, would it say what our person is? Would it say this person name is? Or would it say fellow? Would it say person or fellow? If I was to say for person in people, person print person dot info, right? What would it say for Mr. Bienvenido? Would it use the parent's info method, or would it use its own info method? Right? Right? Everybody sees that? Does everybody see that? Yes. So here, if you option click on person, it's a person. We agree, right? As we get into printing the statement, it uses its subclass info, assuming it overrode. Assuming it overrode info. Yes, sir.
Just to track that, when we put the names in the array,
Yes, exactly, exactly. So Mr. Christian is saying, if you option click on the array here, if you option click on Tom, you see Tom is a person. You option click on John, you see John is an employee. Do we see that? If you option click on Bienvenido, you see he's a fellow. So here I see it's a person, everybody. But when I'm about to print that statement, it prints based on if you overrode info. If you did, it takes that print statement. That is the basis of what polymorphism means. It changes its form based on the context.
it's like a temporary, just to make that array work, and then call it again.
It's not temporary because it prints out exactly what it is, right? So that's not temporary, that makes sense? But yeah, but based on the context, it will change its form.
Yeah.
Right? The context of that people array there is person, or everything is person. When I'm about to use myself, I use my own default values, if I have. If not, I use my parent. So I could change forms based on what I have, or what the context is. What's that? Yeah, very good. Cool. So now let's go ahead and print. We didn't assign it, sorry.
We never assign.
Oh, sorry. What am I doing? Oh, yes. I'm going one step ahead. Where's my people? People. Where am I? Bienvenido, person. No, I think we're.
We never gave them
Oh, I didn't give Bienvenido anything? Oh, sorry. Sorry. Let me give you a name. Apologies, sir. Nameless. Bienvenido here. And John, give John a name. And give Tom a name. The ages could default to 21 for now. Right? So we see that this person name, right, this person, Tom is a person, iOS developer, right, is an employee, and Bienvenido here is a fellow, right? So each got its own subclass or overrode function. Do we see that? Do we see that? Okay. So that is the basis of polymorphism. That's why I said earlier, it's hard to, well, you have to explain it in the interview if you get there, but explaining what polymorphism is to somebody seeing it for the first time is harder without doing an example. Even doing the example, after a couple of days, you'll be like, how does polymorphism work again? Right? So really come back to your notes, right? Test it out yourself, but that's what polymorphism is at a high level. And we'll be using it as we go into app development. We have a subclass or a superclass, it's a view controller. We have our own view controller. We could take traits from our parent. We could change forms based on what's happening. So that's polymorphism, changing form based on context. Yes, sir. You didn't get an error. Where am I? Print. Oh, print this guy. Print. 1 second. No, we're printing it twice. Sorry. We're printing it twice because the thing prints already. All right. That's why it prints. It prints like an empty function. It prints void because that returns void. It doesn't return anything. So just remove the outside print statement. Sorry about that. No, just update it to person.info. Mr. Christian? Right? Because our function doesn't return a value. Right? And if you say print function void, it returns you that void empty bracket. All right? Okay. Let's go back. Just remove, update your function to say person.info. Okay. If you have print embedded there, it's going to print empty function. All right, cool. So let's move on to the heart of classes, the difference, one of the heart. We've seen inheritance, that's different, right? Structs don't have inheritance. Let's see all the differences. If I have it here, great, perfect. So now let's see structs. Let's say structs are value types here, meaning assigning a new variable assigning a new variable. That new variable gets a copy of the original. That's what we said yesterday, correct? Of the original, changing the copy does not change the original, right? That's the heart of value types. Yes? Right? That's the heart of value types, right? Value types means if I have struct A, I create a new struct instance B and I assign A to B, right? Does B change A? No, right? We saw that yesterday. Now with classes, quickly we'll see maybe where we headed here. Classes are not value types. Classes, where we read it earlier, classes are reference types. Anybody want to explain to me what that means? Because we read the lesson, right? We saw that part there. What does that mean? Classes are reference types. I'm seeing the same hands up. Oh, Lydia, go ahead. Okay, so when you reference something, you go back, right? So you change, if I change my name on a reference, right, that changes the original, right? You have a reference to my object. We now have references to the same object. What you change, I also get the change, right? That's like, take GitHub, for example. We're working on master. We're all working on the same repo. You push a change, I see that change. I push a change, you see that change. As opposed to forking, right? Forking is your own copy, correct? But with reference types, as you pass objects around, the reference is the same. Regardless of who changes it, we all see the same reference, right? Take an example here. I have this whiteboard. I put my name on it, Alex, right? I pass it around to Luba. Luba writes her name on it, right? So Luba writes her name on that object. The object is a whiteboard, right? It's not a copy. I did not give Luba a copy, right? Yesterday we gave copies, assuming we gave copies. Everybody has the same copy, correct? They do whatever on their copy, that's their copy. That is structs. Classes, I have an object. It is whiteboard. I put my name on it. Luba has that object. She puts her name on it. What happens to that object? How many names does it have on it? 2 names. Everybody sees that, right? You pass it along to Kelby. Kelby writes his name on it. So right now we're all referencing that same object. There's only one whiteboard passing around. Everybody sees that. That's the basis of what reference types means. We all have references to the same object, right? If there's 36 of us here, we have one object, we all pointing to it, we all writing our names on it. One object exists, right? Does that make sense? We all pointing to that same object. That is the big differences between classes and structs. That's what you'll have to be explaining on an interview. What are the fundamental differences between classes and structs? Right? One has copy, it passes copy, it doesn't change the original. Value type, that's what it is, value type. The other, references, references point to the same object. If I say variable A equals to something, and I go ahead and I say variable B gets A, variable B changes, whatever it changes, A also gets a change. Everybody with me? Cool. May I have my whiteboard back? And I got my whiteboard back, and all of a sudden I have two new names there, right? Maybe I didn't want new names there, right? So that's the pros and cons of having references, right? Whoever has a reference to you could change you. Now be very careful there, right? Whoever has a reference to you could change you. You may not want that in every instance, right? You may want your own copy, struct. You want anybody to change you, like anybody who has that game playing to update the score, a class. Everybody with me? Right? So depending on the context of the object, you might want to pass by copy, where whoever has that copy has their own copy. Or, for example, if everybody's collaborating on the same artwork, right? Everybody's collaborating on a notes, for example, right? Like a Google Doc. You might want everybody to have the same reference, right? I changed one paragraph. Somebody else comes in, they edit it. That's not copy, that's reference. Everybody with me? So it depends on the context. If you're playing some game and you want to keep tally of one score, the highest scorer, that's a class there, right? Everybody has that same value throughout. So that's a fundamental difference there. So classes are reference types, right? Multiple question, yeah. So you have to really think of your code there, right? Before I start myself, do I want to keep the original reference somewhere stored, right? That's where you have to really think of, do I want to struct or class, right? Because to go back, you have to know who did the change. You see what I'm saying? It's like with GitHub again. Like if you have everybody pushing to master, which is very risky, you have to revert. Like who made that last change? It becomes tricky. So be careful there. Does that make sense? All right, so here multiple instances point to the same object. Meaning object B can change object A, can mutate. Okay, we'll see that in an example. We'll create an instance of a fellow called Anna. We'll say Anna.name equal to Anna. Here. So far, so good. If I say print name, print Anna.name, I get Anna. Everybody? Right, so Anna, print name, it's Anna. So this is, let's go up and say, creating an instance of fellow named Anna. We'll go on, we'll say let Luba. Now we assigning, so here assigning Luba the Anna object. So here, Luba gets Anna here. If I say print Luba.name, what's Luba's current name? Anna, right? Right, so let's print it out. So here we have Anna again. So far so good? First time Anna printed her name, it's Anna. Now Luba printed her name, it's Luba. I mean, it's Anna, sorry. It's kind of weird, right? So we want to say Anna or Luba, go ahead and update your name. So Luba, change your name to what your name is. Your name is Luba. Great. Question becomes, what is Anna's name? If printed, right? If we were to say print Anna.name. What is Anna's name currently? Wait, raise your hands. What's Anna's name? Matri, what's Anna's name? Let me scroll down a little bit. So we started off, we said let Anna, assign Anna fellow, or rather create an instance of fellow named Anna. Anna.name is Anna on 126, right? Print Anna, here we have Anna, here. We went ahead, we created a Luba instance, we assigned Luba Anna. We said print Luba's name. Luba name is Anna here. So far so good? So far so good. We kept going. Now we said Luba.name is Luba, right? Her name is Luba. If we were to print Luba.name, we agree it's Luba, correct? Great. Now the question becomes, what is Anna's name? We haven't done Anna.name. We haven't changed Anna's name. What is Anna's name now? It's still Anna, right? Anybody else? Without running the code. What is, don't run the code, Mr. Eddie. I see you. I see your fingers. Okay. What is Anna's name? We're heading, what is Anna's name? Anna, right? Anna's name is Anna? All right. So let's run it and see what's happening here. Whoa. Anna's name is Luba. Right? Ooh, we didn't see that yesterday. That's weird, right? That's part of it, right? Because now, look, we created an instance of fellow. Right, everybody? We created an instance of fellow called Anna. What did Luba do? She didn't create her own instance. She didn't create her own instance. She got assigned Anna, which we saw in structs, different result, right? Same thing as in structs. We assigned Luba Anna. Right now, they're both pointing to what? The same object. They're pointing to the same object here. So both Anna and Luba are pointing to the same object. Remember when we had the whiteboard? I did not create a new whiteboard and give it out to Luba, did I? I assigned Luba the same whiteboard. Everybody agree? Luba went ahead and she wrote her name on it. So this is the same thing we're doing here on line 130. Right? Luba is getting the same reference that Anna is pointing to. So now anything Luba does, Anna gets it as well. Luba went here, she said, hey, my name is Luba. Same reference, same whiteboard. Basically what Luba did here is erase the name Anna and put her name on that whiteboard. Yes, you could say that. Same instance, same object. Because we only have one instance here. We only said fellow, bracket, fellow, parent, only once. So it's the same object of the same fellow. Same object in memory. Same whiteboard. We did not create two whiteboards. Do we agree? That's the harder concept to get there with classes. In structs, Luba would have her name Luba. Anna would have her name Anna. Everybody see that? Right? Let's see what it looks like. Actually, I'm not going to do it because it's going to be harder to visualize. We did it yesterday. The same code we did today, we did yesterday, different outcome. I want us to understand that. So we have two different playgrounds. Really understand what's happening there. We did the same thing that we did yesterday. Everybody agree? Different outcome. Because yesterday with structs, they were passed by copy. I kept my own whiteboard. I gave Luba her own whiteboard. Everybody agree? That was yesterday. Today, I have one whiteboard. I'm passing it around the class. That's passed by reference. Same object. Right? So that's classes. That is reference type. Yes, sir?
So the subclasses, if you edit the subclasses that are part of the superclass.
Any class is reference type. Doesn't matter. As long as you assign some object to some other object, it's the same reference.
Yeah, I mean, if you change those subclasses, they don't affect each other, just like objects, right?
If you change the
Like
subclasses.
when you change fellow, it doesn't affect person or employee, right?
No, it doesn't. No.
Just the object.
Just the objects. And if you do, the minute you assign an object to a next object, they're pointing to the same thing. Talking about that, I want to show us one thing here. Talking about object identity. Let's see. Swift provides a way to check for object equality or identity, right? Using 3 equal signs like that. Is one thing, are those two things pointing to the same object, right? Swift enables us to see that, to know that. Is Luba and Anna pointing to the same object? Are they pointing to the same whiteboard? Yes. In terms of like terminology, yeah, you could say that. But instances is like, yeah, you could say that. All right. So here, let's see. If Anna triple equal sign equal to Luba, then print both objects are pointing to the same reference. Let's see if this is indeed true. So here, they're both equal. Equal. Same object, same whiteboard. Period. So that is the object identity syntax. There's two things, two classes. You can do that on structs, right? If it's two structs, you'll get a compiler error. Only on classes, you could have that 3 equal sign. So only available. Object identity syntax. Only available. I'm sorry? Compatible? What do you mean? You could write that. Available is good. It won't. It's gonna be a compiler error. Yeah. Only available on classes. Period. You can do it on enums. You can do it on any value types. Only reference types. And classes are reference types. Only classes are reference types. Yes, sir.
Can we maybe see an example where it was like, I get how it works, but we do an example where it's actually set on purpose.
What?
I don't see what like where we would.
Or it depends. Like if you want to, again, that's like in code. When we do more code, we'll see those things. Part of all the lectures is showing us what's available to us. And then when we get to actually doing a project or doing an assignment, an assessment, it's like, hey, oh, I see that component separated by already. I get how I could use it. You come to some case where you're in an app, you're like, hey, I want to change something, but I want to make sure it's the same object. So you could say, hey, is Anna equal to Luba? For example, you want to add a fellow only if it's, or you want to remove a fellow from an array, only if it's the same object, pointing to the same object. You'd go through it with an array, with a for loop, and say, hey, only if those two things are pointing to the same object, remove it or do something to it. Cool? Yeah. But now we know it exists, And we know if it's true, that means they're pointing to the same exact object. Does that make sense? The same exact whiteboard. Cool? All right. Very good. Yes, sir. Yeah. In a template, in what sense? A template in what sense? You want to get like a default game. You'd either start out with a protocol, which we'll talk about, or you could start in an object-oriented way where you have a base class as the template, and then you inherit from that base class. One of the two ways. Either a protocol-oriented way, where you have a protocol, it has a template of what you want, or an object-oriented way, where you have a parent class like a person, and then you have employee inheriting from person. Only those two ways. Any other way is not advisable, if that makes sense. Cool? Like when you start submitting code and then instead of creating an object or a protocol, you create a dictionary of stuff, right? You're like, oh, I'm creating a fellow. It's a dictionary, right? It's not a struct or a class. It's a dictionary where I find the age by using a key, right? That's not acceptable. Does that make sense? Like whatever we did prior to seeing object-oriented principles, you don't use. So anytime you're going forward, you're thinking of some app you want to build or app we give you guys to build, the basis should be, for now, we haven't seen protocol, but for now it should be object-oriented programming. I start out with a calculator brain. It has the basic functionalities of a calculator. I get any functionality I want from that brain. Does that make sense? Yeah. It's not a dictionary, it's not a tuple, right? Does that make sense? Because you could expand, you see how we could expand on a struct or an enum or a class. It becomes very extendable. Very good. Cool, cool, cool. So let's keep going. All the differences between classes and structs. Here we spoke about a member-wise initializer yesterday, right? Right? Everybody remember? Let's review here a little bit before we go into it. Who remembers member-wise initializers? Yes, sir. Yeah, when you're about to create an instance, you open the parents and you get the default variables, right? Everybody, member-wise initializer, right? Yesterday, it's in there. Okay, so basically if we have a struct here and we have dog, like that, and I say dog has a breed, string, and age is an integer. So this is the dog, right? This is the basic struct. It's a dog. We could go ahead. We'll get to it. We'll get to it. We haven't seen anything yet as that. But we saw it yesterday, but we'll get to it again for review. Here we have a French bulldog. That's you, huh? That's your favorite there. I can tell. All right, so here we have a French bulldog. We create a new instance of dog. This is the member-wise initializer I'm talking about. When you say open parens and you get an initializer, meaning all the properties available to us, that's a member-wise initializer, only available on structs. Right? We'll see what we mean and the differences. Because in our struct right now, we do not have anything that says init. We'll come to that in classes after this example. But here we have dog, open parens, I get a list of properties that I need to fill out. So I say breed, say French bulldog here, and age 7. Right? So here, creating an instance of dog using the member-wise initializer of the dog struct. Right? And then we'll say only structs provide member-wise initializers. Now let's see the difference now. So if we have a class, call it game, all right? So game we have here has a name, string. Game has number of players. It's an int. We stop here. Look at that. Difference number 3. Class game has no initializers. Why? We do not have default values for the properties. If I put default values for the properties like this, it's going to compile, right? Error goes away, and it's all good. So if you see this on some coding challenge or assessment, does not compile. If you see class here, that's how you should read the code. You see a class, it has a name, this is fine, this is fine, this is good. You come here, you see var, you see name, you see string. There's no value after string in a class, it's a compiler error. Right? Compiler error if class does not provide default values for all properties. Right? I can just say I want to do just a string like that. It will still give me a compiler error. All the properties needs to have default values on a class, or else it will not compile. Right? Look, this is the same thing we did. 162 to 165 is the same as 152 to 155. Do we agree? The only difference, one is a struct, one is a class, correct? Correct? Our struct provides us this default member-wise initializer here. It gives us this for free. We're able to do this. It's an initializer. Initializer is a function or a method that initializes. It gives all properties values. Right? So here, in our game here, we do not have the option to do, like if we go down and create a game instance, if we create a game instance here, say game, and type in game, look, we have no options. Everybody sees that. We have no default member-wise initializer. We have no member-wise initializer on a class. Does not exist. How do we do? What do we do? How do we fix this? Right? Again, you could fix this by having default values. We all agree? If I have default values for name and number of players, it works. Everybody agree? Default values meaning I say equal to something, equal to empty string, equal to 0. That works. It compiles. Compiler warning goes away. But compiler error goes away. But if any of my properties have no default values, I have to provide what's called an initializer for it. Let's see what that looks like. So here, let's say properties. This is properties. And here, we'll have initializers. You could have many initializers. Today we'll just see one, Monday we'll see more. So here I will start out by saying init, open parens, close parens, open curly, close curly. Right? It's a method, but it doesn't have the funky word. Right? It doesn't have the funky word. The compiler knows what it is. So now you get more errors. Return from initializer without initializing all. You see that? All stored properties. I need to initialize all my default values. I need to give them all values here. They do not have values. So what do? It's a method. It could take in arguments. In our case, we need to make sure it takes arguments. So we start out with argument names, name, the type. What type are we expecting? String. Is that it? We need to have number of players. You could name them differently. Get in the habit of naming them the same. And here we have int. So far, so good. Next compiler error. Return from initializer without initializing all properties. Same error we had before, because we're still not done. Now, our favorite keyword, self dot name equal to name. Self dot number of players equals to number of players. The compiler does a good job of syntax highlighting it for us. The green highlight here is the internal name, our internal name, right? We said self, we used self in enums before. We said self is the instance, right, everybody? Self is the instance that's creating game. What do I mean by that? When I say let game, game is the instance, right, everybody? Everybody, game is the instance. I say game equal to game parents. Look, voila, I got my initializer. My initializer now is this one here. It expects a name. It expects number of players. So far, so good? So this works on the instance. So now it's going to say game. This is going to be changed when the compiler sees it to game.name. Everybody? Right? So this is going to be equivalent to saying game.name equal to something. Yes, sir? So you want us to type this over? So self dot number of players. Right? You good? Okay, enter equal to number of players. One is local, one is the variable coming in. Right? That's why you do use the self keyword. Right? The local one is the one highlighted in green. Right? Local to us. And the one that's not highlighted in green is the one coming in from the function parameter. Right? The one coming in here, this one. So there's two. There's this one that's coming in from game, and there's the one we set it on ourselves. Cool? Those are the two different ones. And I really don't want to change the names. I want us to get in the habit of it. Even if it boggles your brain, I do not want to change those variable names. I don't want to say name one and then name something else. Get in the habit of doing this. This is the code we'll be writing. I don't want to say, oh, this is confusing, change number of players to something else. You can, but really it's important to get used to knowing the differences between this self.name here. This self.name is setting yourself. The name coming in here is the name coming from whoever is creating that instance. Everybody with me? All right, we'll do it and we'll see what it looks like. So here we'll have let game. Now we have our initializer. We press enter. Right? We put in some name here, basketball. Number of players, 5. Right? So look, let's start with the instance. So here we're creating an instance of game. Right? Creating an instance of game called basketball. We'll change the name. So change game to basketball here. So we're creating an instance of game called basketball. Great. We start off with the type. The type is game. So far, so good? We have our initializer, which takes in 2 arguments. So far, so good. Stop me. Stop me. Right now, change game with the little g to basketball. We changed that already. Game is using the initializer. Only one initializer it has right now. This is the initializer here. We created it. Let's walk through it and then you'll ask questions. Let's walk through it first.
I just don't know the word for it, when something's being
Created,
instead of something.
instantiated. So here we're creating an instance of game called basketball. We start off with the type that we're interested in creating. We're interested in creating a game. So far, so good? Mel? We're interested in creating a game. We say game, the name, the type, followed by parents. It gives us the initializer. Not by default, we have to create it ourselves. Correct? Correct, Ian? We have to create it ourselves. It expects a name, argument label. We have the name. It expects some string. Do we agree? Everybody. It expects an integer. We pass it 5. So far, so good. Now let's go to the method, to the initializer. It sees name. Name here is what? Yeah, but when I call it, what's name now? Basketball, right? So what's name here? Basketball, right? So let's hang out together. So here, this becomes game or basketball. This is very similar to this. This is basketball.name equal to basketball. That's what happens here. So self is what? Basketball. Because basketball is the instance, right? Everybody? We're following along, right? So self is basketball. That name is the property here. That name. Everybody? Everybody. All right. What's name? Basketball. Right? That's that. Let's go to step 2. Step 2, what's self? 0, what's self? What is self?
What is it's what the person inputs.
Self is the instance. Self is the instance. And if we look down here, what's the instance? Basketball. So we replace self, visualizing it. Self becomes basketball. That's the instance, right? Right? And then we have number of players.
So we always use self dot equal to the use and then underneath it give it the instance and so we call that.
We do not write this in there, right? That's just like showing us what's happening.
No, I'm saying we usually use self.
Yes,
Dot.
exactly.
And then the behavior name with the string.
Exactly, exactly.
And then underneath that.
Because not using self here, it's kind of weird and the compiler will give you an error, right? I cannot convert assign number of players is a let, right? It gets very confusing. It throws a compiler error. What do you mean? So the meaning is I want to change number of players on myself or assign number of players to myself. So here, the self keyword is used and self represents the instance name. So basically, basketball, right? Yes, sir.
So in it is a method.
Init is a method, yes.
But it's already, you wouldn't have to create it like put func before.
No, there's no func there. It's just init.
And then, so it basically,
No, come on. Go ahead. So init is a method. It takes into arguments, number of players, a name.
now I remember. So what happens if you create another instance of game?
We'll create another instance. It has its own instance. We'll create the next instance. Cool? After this one. So now we have basketball, that number of players. What is number of players here? 5. Very good. Right? Because here I said number of players, I pass in 5. It goes to the function or to the initializer. Number of players becomes 5. Number of players here is 5. Very good. Right? So this is what's happening here. Everybody with me? Yes. We have to. We have to. Because we did not give those default values. And we're also in a class.
But if you were to have assigned the property values, you wouldn't have used.
Exactly. Exactly.
When would that be useful? When would you initialize
Most times you'll find that you start out this way, where you don't give them default values because it's unnecessary. And then as you instantiate them, you give them values. Right? Whether you're getting data from the internet or you're passing in data from a dictionary, which we'll see hopefully today or Monday, right? Does that make sense? Because giving them default values is like redundant almost, but the power of initializers is stronger. Yes, go ahead. Yeah, very good.
So then the browser knows what variables you have.
Yes, because based on the instance you create, our instance is basketball. We pass in our variable, our arguments here, basketball and number of players. Somebody else, give me a different game. Mr. One, give me a game. Yeah, give me a game. Whatever game.
Football?
Football, soccer, football. Yeah, football. I like football. The one with your foot, right?
Yeah.
Yeah. Okay. We all know which one we're talking about, right? Yeah, football is football. There's only one football. The one you play with your foot, 100%. Cool. So we have football here. It's a game, right? The name of it is football. Number of players, 11, right? So far, so good. So now we have football. Those are two different instances, right? They're not pointing to the same object. Everybody with me? Right? So I changed football. Football is football. If I did this, like that, basketball, then they would be pointing to the same object. Everybody with me? Because you assigned it. We see that. But now this is its own instance. There are two different instances. So here, we've created two different instances. One is basketball, one is football. Awesome.
Okay, so right now they're not facing the same object, they're two different.
Two different objects. So I say football dot number of players, somebody got subbed out, we have 10. It's not going to change basketball. All right, does that make sense? All right, so this is good. This is good, this is good. I want to show us one more thing and we'll probably wrap up today.
So subclass would inherit the initializer as well.
Yes. And you could make initializers required too. Like you have to, we'll talk about initializers on Monday. It's too much for today. I want to just get us up and running with classes and see how we could work with classes, with dictionaries and classes. Yes?
So if I run an initializer in any class, I wouldn't be able to do like football.name.
Yeah, you could do football.name. It's a variable here, so football, let's change it. So you want to do, let's go down here and do, so accessing properties, right? We could access properties, change them, as long as they're mutable. So here I could say basketball dot name is NBA. So far so good? And now I could say, it would be nice to have an instance method called info here. Let's create an instance method. Bear with me, let's go up. So right below our initializer, we'll have methods. So methods here, and let's create a method called info that gives us information about the game. And here we'll print the name of the game. In that case, name has number of players. So yeah, NBA has, basketball has. Okay, cool. So here we have an instance method. Instance method. We've been using like info, which makes sense, like giving information about this particular object. Yes?
In this case, will info, like, be as the same, would it affect anything on the game?
We haven't inherited. Game is not inheriting from anything.
Okay.
All right? Game is just game. Cool. So we have, let's go to your question, Mr. Greg. So everybody created the instance method info, correct? All right, let's go down. So we changed basketball name to, so we could say basketball.info here to see what it is before. So basketball.info, if we run it, first off, we have basketball has 5 players. So far, so good? Right? Because that's how we instantiated it, right? We said basketball. Now we went ahead, we updated the property name, right, using dot syntax. And now our basketball info becomes different. Now we have NBA. Cool? So as long as your property is mutable, you could change it using dot syntax. Cool? Very good. Yes, sir. All of the variables. All the properties, yes. You need an initializer if all the properties are not initialized. You still need an initializer. Yes, exactly. So Eric brought up a good question there. So if I have 5 properties, 4 of them are initialized, you would need one for the 5th one, an initializer for the 5th. Yeah, in that case. Or all or only, but you have to do the last one. Number 5 needs to be initialized. So you could have an initializer only taking one argument. Very good question. What's that? For classes, yeah. Go ahead. Yes. Yes. Somehow, either through an initializer or with an equal sign. Yes, sir. What's that? To store variables, yes. So we'll talk about more properties next week. There's like computed properties, which returns a value. It has a value, it returns a value. We'll talk about computed properties later. But yes, good observation there. All right, cool. Looking good, Charlie Brown. Creating instances from... We'll talk about the initializers on Monday. Too much today. Let us look at... No, I need a title. New title. What title is this one? What do we do? This one was initializers, right? Intro to initializers. That makes sense. Introduction to initializers in classes. Structs could also have initializers, by the way. But they have the default member-wise. What's it called? Member-wise initializer on structs, right? Everybody? All right, so cool. Introduction to initializers. We'll do some more initializers on Monday. Let's keep going here. Get your header. And here we'll have a new topic. Creating instances. Let's put initializers on it. Creating instances from a dictionary. The earlier one, TIFF, was using initializers on classes, right? This one is creating instances from a dictionary. We know what instances are. We're comfortable with using the word instance. We know what it means. So creating instances from a dictionary. Great. We'll start out with a class. We're doing classes here. It's going to be called playlist. A playlist has a name, string. A playlist has track count. What type is track count? Integer, very good. A playlist has a description. Type, string. Great. What do we need now? What do we need? Why do we get a compiler error? Because we need to initialize them according to Chelsea. Who wants to come type this out? Mr. Oscar. It's okay, we're here, we're a class, we're a team. How do we start an initializer? How do we start out an initializer? What else? Open parens. What's the first property here we expecting? So type a name in the parens. Colon. What type is it? Space. String. What do we do after the string? Comma. Next type is track count. And we want to name it the same. You could name them differently, but really get in the habit of naming them the same. That's where the self keyword helps. The self keyword differentiates
We do a description. and
So what are we missing here? Track count is missing something.
stuff.
What type is it?
It's a
So
s-
colon.
Oh,
Colon. Int. Very good. And description
it's a string, right?
is a string. Very good. Now we have open curly. Enter. This is the. Great. What do we do now?
Self.name.
Go ahead. Self.name. So self here is the instance, right? The instance creating this playlist. So self.name. Guess what? Equal.
String, int string.
In that case, you telling the user you don't care about what they're passing. So you want to take what they're passing, which is name.
Without the
Yeah. Very good. And next one, track count. Same thing, self.
try count, right?
Very good.
It has to be a
Yeah, enter. That's fine. Good. And last one,
description.
yeah. Do a description somewhere? Weird. Oh, over here. That should be one. Take out the S over here. Yeah. Description. Perfect. Okay. Good. Compile everything. Thank you, sir. So here we have our completed class, right? We have 3 properties here. So those are the properties. 3 properties. And here we have our initializer. Awesome. What can we do with that? So say we were given, this is our class, it's separate from everything else. Let's create a dictionary here. We'll call it playlist. It's a dictionary. We'll type annotate it. The key is a string, and the value is any. We haven't dealt too much with any. We'll deal with any. It's any. It could be a string. It could be a bool. Could be an integer. Could be our custom type. Could be a programming language. We don't care. It's any type. Everybody with me? Our value could be any type. We agree, right? That's what we specified to the compiler. Let's go ahead and populate our dictionary here. So we'll start out with the name of the playlist. Name of the playlist in that case, we'll say best. So far so good. Comma. Next up, we'll have a track count. And that's an integer, right? So we have 128 here, comma, enter. Next up, we have description, which is a string. We'll just put in awesome playlist for now. Great. So far, so good. So here we have our dictionary. It has 3 values. It has a name, track count, and description. So far, so good. Good. Let's go ahead and populate our, let's create rather. So here, write a function. Write a function that takes a playlist, or rather a dictionary of type string any, and returns an optional playlist. Yes? Okay, we'll come back up. So here we created a dictionary, right? The dictionary, the key is a string. The value is any type. Any implies any type, right? Here I could put in a string, for example, but this is not going to work, right? It's not going to work. Why? Why does it not work? Because we have an integer here, right? So if we have mixed values, we say any instead of a string. Good question. So the compiler expects any type. It could be a bool. Our type, I mean our value, could be any type. I could have an integer. I could have a string. So far, so good? I could go on and update my values. If I have a bool there, I could have a bool. Right? Yes?
So we're just putting these keys, like the keys that we're using for our dictionary. They don't like it's not like the it's not like they it's not like they go in and look for those specific names that we give.
We will. That's the exercise. That's part of the exercise. Given a dictionary, make a playlist.
So they will say if
We're gonna get there. We're not there yet. So for now, all we have is a class playlist. It has its properties. It has an initializer. Next up, we have a dictionary, right? A dictionary of key value pairs, right? That happens to match the same as our playlist. The next step is going to be to write a function that takes in a dictionary and creates a playlist and returns that playlist to us. So far, so good? All right. Cool. So here, write a function that takes a dictionary and a dictionary of type string any and returns an optional playlist, right? Good. We have a playlist. We know what the playlist is. It's a class that we created here. We know this is a dictionary where the key is a string. Those are all strings. And where the value could be of any type. I could have a string as the value, or I could have an integer. So far, so good? I could have a bool. Is top 100. I could add that there. Right? As a matter of fact, let us add that, if you don't mind. Let's update our playlist. So var is top 100. It's a bool. And let's update our initializer. We could use commas, spaces, if you want to organize it better, cleaner. So here I will say is top 100. It's a bool. I'll wait until we update our class. One more thing we have to provide. You see, we have one thing that doesn't have a default value, so we have to also update it. So here we have self.is top 100 is top 100. So we've added a fourth property. So this is false. Let me just take out that altogether, because that could be easily not true at any point. So here we have four properties. We created the fourth one. It's called is top 100. It's a Boolean. So far, so good? So now we have three different types. We have a string, we have int, we have bool. Our initializer now has four arguments, or four parameters. The fourth one is called is top 100. It's a bool. We assigned our is top 100 to whatever got passed in. We have one more error, right? Because the person calling this needs to supply, oh, we haven't created it, good. So we have no more errors. Oh, actually here, let's create one more key value pair. So here is top 100, and here we could just pass in true, like that. So we really see our any, the use of it, right, Chelsea? Right? Because there we have a bool, we have a string, we have an int. So we told the compiler to expect any type. And any type could be any type. I could have a person in there. Right? Like I could actually have a fellow.
oh, okay.
You see that, everybody? I could actually have a fellow, if I want to pass in a fellow. Right? A fellow is an artist, we could pass a fellow here.
Oh, so
like the type itself. Yeah. So here, what do we have? True, right? I mean, not the fellow, but I could have, what fellow did we create? We have bienvenido, right? So I could pass in like bienvenido like that, right? Does that make sense? You said no, right? That's fine. Bienvenido is a type. The type of bienvenido is a fellow, correct? 128 is a type. The type is an integer, correct? So I could actually say bienvenido, give it something, right? Some value, but like any type. Yes, question. We said true, right?
I'm getting, for, self that is top 100 is top 100. Yeah, I'm getting that it's used itself, it's assigning a problem.
Did you update the init like this? Does it have is top 100 bool? Thank you, Sarah. All right, cool. So we all good. We all up to par with the code so far? All right, let's continue. Write our function. We start with the fun keyword. By the way, we need to start getting in the habit of writing over the weekend. Please do me a favor. Grab 3 questions from previous labs and practice writing the functions by hand. Because next Wednesday, I think engineers are coming here, and we might do some whiteboarding. Everybody? Wednesday is PS, right? Yeah, in the morning. So get ready for like whiteboarding practice. So really practice going away from the computer and writing the function. Hey, a function that takes in 2 integers and it returns whatever, an integer. All right? Get in the habit of getting away from the computer and solving the problems. Like we did with the pair programming. So on Monday, we might try to squeeze pair programming in there so we get more practice for Wednesday. Cool? So here, write a function. We'll call it create playlist or get playlist. Let's call it get playlist. It just gets a playlist. So here, good. So get playlist takes in a dictionary as we promised. What is the type? The type is string any, right? So far so good? What does it return? Did you say ls? Oh, sorry. It returns an optional playlist, right? So far so good? Yeah. Cool? Questions? Wow, it's getting hot in here. Tiffany, you're burning me up. This is good? Man. Oof. All right, so we have our dictionary. How many values do we have? How many properties do we have? 4. So we need to extract 4 properties in order to create a playlist. Do we agree? Do we agree before I move on? Right, so let's get that. So we need a name. That's just a question. The question says return a playlist, just return as a playlist. If you did not get a playlist, it's nil. If I wasn't able to create a playlist from that dictionary, it's nil. Because there's no guarantee that the dictionary does have a playlist. All right, cool. So here we have name. How do we access the keys in our dictionary? How? What's the syntax?
Oh, the colon.
The colon? Dot keys? Dot name? How do we access the key? How do we access values in an array? Square brackets, right? So here we have square brackets and the key name is name. I know so many things. Why name? Because this is the key. Everybody? Right? Key value, this is the key. How do I access values? By subscripting the name, the key. Yeah. We'll use nil coalescent for this. Let's follow along there. This is good. Good questions. So here we have our dictionary. We want to access name. Everybody with me so far? Right? There might be a value or not, right? What does name say? If you option click on name, what do we get? Come on, say it. Optional what? What's here? Optional any. Can we use optional any on our playlist? Does our playlist take in any type? Really? Let's look at playlist.
Oh, no, playlist doesn't take any on.
Like this name should be a string, right? Everybody. The name should be a string. The track count should be what? Description should be? Is top 100 should be? Boolean. Very good. So let's see. So any doesn't work for us. We saw what was called typecasting. We saw that during the set lecture. We saw typecasting. Right? Typecasting, we said as question mark. Right? We said that's optional casting. So we need to optionally cast this to the type we expect. If you bang it, it's going to crash if it's not the type. So be careful here. So now, after our subscripting, I will say as question mark the type I expect. I expect a string. If we option click on name, what is the data type now? Optional string. So far, so good? Does my playlist take an optional string? No, right? If we go back, this is not an optional string. So far, so good? I'll write it out. I'll write it out. I'll write it out. I'll write it out. We'll write the notes. But is this an optional string? So we need to fix that. How can we fix that? Nil coalescent. Very good, Chelsea. So here we'll nil coalescent with some default. I'll say no name available. Now, if we option click on name, what is the data type? It's a string. We're happy, right? Because the string should be, name is a string. Now let's talk about what we're doing here. Let's do it. A lot of things are happening here. So here we're accessing the name key in dict here. That's step one. What are we also doing? We're typecasting any to string using optional downcasting, which is as, well, let me be careful there. Let me not put that. This is as like this, right? So that's the syntax. Everybody with me? Everybody with me? Okay, and the next step we said, the last step we did was use or used nil coalescent to unwrap optional string. Right, so those are what we did there. The first one, accessing the name key in dictionary, like this, right? We had our name key, like that. Second step, typecasting. Yes, use typecasting, 1 second, use typecasting of any type to string type using optional downcasting, this guy. All right, yeah, question? This as question mark here? That would be almost the same, yes. Okay, so again, we're not banging here. If we did this, this would be force downcasting, right? With the bang, this is force downcasting. You see, the minute you force downcast it, you do not need the nil coalescent anymore. Everybody sees that? Everybody sees that? But we know the downside there, right? If name doesn't exist, it will crash. Everybody with me? So please, never, never, especially dictionaries, never, ever force downcast a dictionary key. Very, very dangerous. It might work one day, next day, the API changes, something changes. It's going to crash your app. Boom, because of that one bang there. So use optional downcasting when going through a dictionary. And let's fix this here. Great. Yes, sir. Where's the question coming from?
No, they were saying use optional downcast.
Yeah. Well, we have it here, right? Optional downcasting. This is the as question mark. Yes, sir.
This is primarily used when like the or can they cast before it's like anything? Or
When you expected a type, like in that case, we're expecting a string, right? But it might not be a string. So if it fails, then it goes to our default value.
I mean like we're checking for any value, so is that
Yeah, exactly. Because it's any, we want to cast it to the type. Yes. Because we can work with any as is, yeah, very good. Now let's continue. You guys do the rest of the three. So here, the next one, I'll start out by saying what it is. Was it? I forgot. Track count? So do track count. Do track count. Do description. And do is top 100. Great, that's good practice. And at the end of the day, we will create a playlist here. And we will return the playlist. Yes?
So that process right there with the name as, is that via a two-step process unwrapping the
Yeah, as opposed to, like in that case, you don't want to do optional binding, right? You want to get straight to the point, right? You want to unwrap, you want to typecast it to the type, and if it doesn't exist, just give it a default value. Cool? So great use case of nil coalescing. You'll see that a lot of places in different codes as you go along the way. Now we have practice. 4. Plus you're making the playlist. Are you making the playlist? Yeah, make the playlist. And when we're done, we'll just use it. When we're done, we'll say let playlist equal to get playlist, pass it some dictionary, and just print playlist dot name, for example. Playlist not created. Cool. I gave you guys some boilerplate code. So you will do 28 to 20 to 230, 228 to 231. You'll complete that. You will, well, we created an instance here, and then we'll print out what the name of the playlist is. Right? Yes, sir. Yes. Oh, sorry. Why are we letting playlists do? First of all, do the steps first before you come to let playlists be something. Use typecasting and nil coalescing to complete step 228 to 231 to 230. And the playlist equal to something, that's where you create an instance, right? So you say playlist.
Oh, okay.
All right. Very, very good. Do is good. Do it, and then you'll see the questions are going to get answered. Yeah. If you didn't coalescing and type it in, what's the default? So the string of it. That's fine. That's right. The right question? You're creating playlist from our class. So you say playlist, you create an instance of playlist. Cool? So you start writing playlist, open parents. With, with line 231, we created an instance, right, everybody? Create an instance of playlist. We should know what that terminology means now. If somebody says create an instance of a class, how do we start? With the class name, playlist, open parens. It gives us the initializer, and we fill out everything we have up top with the name, the track count, description. So playlist, you create an instance of playlist. So with track count, we have, I will go ahead and cheat a little bit here. I'll copy, paste. But you get in the habit of typing this out, please. For that, we have track count. Track count is an integer. And default cannot be a string. Do we agree? Right? It needs to be some sort of integer here. So default 0 is good. For our description, the key is called description. Why is it called description? In here, our key is description. So far, so good? Everybody, if you have description with a D, it's going to fail. Do we agree? It needs to be spelled the same way as the dictionary is. So here, description is a string. We say no description for the default. No description is available. It's fine here. For top 100, I will say for the key is top 100. So far, so good. Yes? This guy is what? What type? It's a bool. What's a good default? False. Very good. Great. So far, so good. Next, how do we create an instance of playlist? I type in playlist. This is my class, playlist. Open parens. I get my initializer. I press enter. For the name, I put in name. That name is coming from line 227. So far, so good? My track count is track count. Right? I could organize my code by pressing enter here. So it's nicer to read, better on the eye. Right? Description is description. And this is top 100. Great. At this point, I am good. I'm using everything. Warnings are going away. I'm returning the playlist at the end of the function. This is a function. Function takes in a dictionary, returns me a playlist. Right? If it doesn't exist, it's nil. Right? So far, so good. And here I'm using an instance. I'm creating an instance. So creating, or not creating an instance, rather, calling the get playlist function, which returns a playlist. Great. So we got a playlist back here. It might be optional. If you want to print it, you have to use optional.name and give it a default. Playlist not created or playlist does not exist. Cool. Let's test this out by running it. And here, we got our playlist back. Because we have the name here, it says Best Pop Songs 2019. Everybody? 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 Do we have an info on our playlist? An info would be good. Let's create an info, and then that'll be it for the day. So let's create an info inside my class playlist. Let's just create an info here. Yeah, exactly. So we could say playlist info or just info. Info is fine. Inside of the class, right after the initializer. Right after the initializer. In the playlist class. Right after the initializer. Remember, initializers, then methods. So instance method here, info. So we'll just say print the name of the playlist contains X amount of tracks. Here we get track count. And we could put in a description there. Cool. And we could even have an next print statement in there. Well, we could do an if let. So if is top 100, print name is on the top 100 Spotify list. Right? So we could really, again, the thing could get complex, right? It's a complex data type. We have a class here. We could do a lot of cool things. That's why at this point here, that's where you could bring your hobby into coding by just testing things out. If I'm a musician, I could create a class guitar, a struct guitar, whatever, and start putting things in there, right? That's where you really start really loving coding there. So here I have an instance method, is info. I'm printing the name of the playlist contains whatever tracks, the description of it. And if it is in the top 100, print the name is on top 100. So let's update is it true? Did we pass in true? Let's pass in, it's true. So good. So that's going to get executed. So far, so good. Can we go on? Can we move on? Cool? Good? I'll slack it out. Some people are getting hungry. They're looking at me weird. Okay, so let's go on. So now I have, let's just print, instead of the, what are we doing here? So instead of name, just print info. So dot info here. Still returns a string. Doesn't return a string, doesn't return anything. But that's fine, that's still a string. Playlist does not exist. Good. Go ahead and run it. So now we're still printing something. Just remove that print here. Print, this is good, take this out, and then run it again here. Argument pass to call. This is playlist.info. All right, run this. All right, great. So now we got best pop songs, contains 128 tracks. Awesome playlist is the description. And we got best pop songs 2019 is on the top 100 Spotify list, right? So all that works. We were able to get back a playlist, and we were able to use an instance method to print out more information about that playlist, right? Any questions so far? Move back to this guy. Down. Here. There. This is good. Keep going. You're welcome. Cool. Any questions? If no questions, we are good. We are done. The question mark after this guy? Like that? We had it on the, so here it's an optional, right? Remember it returns an optional. The playlist might not exist. Question was, why do we need a question mark after playlist? Why do we need a question mark? It returns an optional. Remember our function returns an optional here? Right? Question mark, Luba. Right? Playlist returns an optional. What type is this? If you option click on playlist, what type is it? So the only way to access a method on it is to use optional or to bang. In our case here, not necessarily, but it could be. Right? That might be on your lab. I'm not sure. All right? Cool? You could change it to not optional. We could remove this optional here. We could remove this optional here, and this is fine. But you might have a case where you have a dictionary that returns you a nil value, because that dictionary itself doesn't have anything valid. So that's most likely the way you write code, especially when you get to Unit 3, where playlists might exist or might not exist. A meaning? That's the logic of it. It could exist or could not exist. Cool? Yes, sir. Did you write out our playlist here in the function? Did you write is top 100 here? Okay, I'll come and double check what you have on there. Okay, cool. All right, so we're going to stop for today.